Morning, everyone. So today, like I said, we will start off with this question. Now, I just want to go over the general way that we answer questions like this, because in the test, the questions that you'll get will not be exactly this one, but the way we solve them should be pretty much the same. The first thing you should do is try and summarize what you are given into a matrix. So it says that the Ace Novelty Company received an order from the Magic World Amusement Park for 900 giant pandas, 1,000 St. Bernards, and 2,000 big birds. Management has decided that 500 of the giant pandas, 800 of the St. Bernards, and 1,300 of the big birds could be manufactured in their Los Angeles plant, with the balance of the orders placed in the Seattle plant. Okay, so if we're to summarize that in a matrix here, the first thing we have are the orders. Okay, so we have some are going to LA and others are going to Seattle. So we have the giant pandas, the big birds, or St. Bernard first, and then the big bird. So if we're to form a matrix, it will look like this. So it says that 500 are going to LA, so we have 500, and there's a total of 900, so that means 400 are here. We have 800 of the St. Bernard are going to LA, and in total there is 1,200, so that means 400 are going over here. And then for Big Bird, we have 1,300 going here, and all together they're supposed to be 2,000, so that means there is 700. Okay, so that's our first matrix. Then the next thing says each giant panda requires 1.5 square yards of plush, 30, just underline it, 30 cubic feet of stuffing, and 5 pieces of trimming. And St. Bernard requires 2 yards of plush, 35 feet of stuffing, and 8 pieces of trimming. And then a Big Bird, 2 yards of plush, 25 cubic feet of stuffing, and 15 pieces of trimming. So now we look at the material and we form a matrix. So we can look at it like this. We have the giant panda, the St. Bernard, and then the Big Bird. So the material is plush, is stuffing, and then there's trimming. So this needs 1.5 here, 30, and then 5. St. Bernard's needs 2, 35, and 8. And Big Bird needs 2.5. 2.5, 25, and 15. Okay, so let me just make sure that that is fine. So we have 1.5, 30, 5, 2, 35, 8, 2, 5, 2. Okay, so these are our 2 matrices. And then the last thing, it says the plush costs $4.50 per yard. The stuffing costs 10 cents per cubic foot, and the trimming costs $2 25 cents. So then we look at the cost. We have the plush cost, the stuffing, and the trimming cost. This one here is 450. Then we have 10 cents. And we have 25 cents. Okay, so those are our three matrices. Please find the amount of each type of material to be purchased for each of the two plants. Okay, so we're going to multiply how many we're sending to each plant by the cost of material. Now, what you want to do is, even if your matrices were just writing this down, even if your matrices were not written like this, what you need to make sure is, because we multiply rows with columns, you need to make sure that giant panda is always multiplying with a giant panda, and a Saint Bernard value is always multiplying with a Saint Bernard value. So for example, what I mean is, if this matrix, I had written it like this, so I put the giant panda here, the Saint Bernard here, and the big bird, and then my values. So I would essentially have the transpose. So let's say I had 1.5, I had 30, then I had 5, then 2, 35, and 8, and 2.5, 25, and 15. Let's say this is the matrix. This is the way that I'd written it. This is for the plush, the stuffing, and the trimming. Now, if I were to try and multiply, see, I have to go row with a column. So the first one, I'd be multiplying this with which is giant panda. That one is also giant panda, so that's fine. Then this one here, I would multiply it with that one there. But you see, this is a giant panda stuffing, and this is a Saint Bernard amount. So it doesn't make sense to multiply them like that. So you test it out. If I write my matrix like this and I multiply row with a column, this one, the first one will be fine because it's a giant panda amount with a giant panda plush cost, so that's fine. But then when I move on to the second element, this is a Saint Bernard amount multiplied by a giant panda stuffing cost. So that matrix wouldn't make sense. So then I would know, okay, this matrix is not the way to do it. Let me try the transpose, and that's how you'd end up with this one. So this one would not give us the correct values. So now to find the cost, because I test when I multiply this row with this column, this is a giant panda amount and a giant panda cost, that's fine. This is a Saint Bernard amount, and the second one here is a Saint Bernard cost, that's fine. This is a big bird amount, and this is the big bird cost. So what I'm getting will make sense. So now we say, to find the cost, so our cost, sorry, not the cost, the amounts actually. The amount of material. Okay, so we will say 500, 400, 800, 400, 300, multiply this matrix 1.5, 35, 2, 35, 8, we have 2.5, 25, and 15. Okay, so we know how to multiply. It is rows times column, and then we add. So our matrix here, the first element, take your calculator. So you say 500 times 1.5 plus 100 times 2 plus 1,300 times 2.5. Okay, so this is 5,600. Then we do the same thing for the next one. So row with the column. So this one here tells us the amount of plush, okay, that we are going to need. All right, because this was LA Big Bird and plush. Okay, so this is the amount of plush we need in LA. Okay, then for the next one, we see again row with column, and that's going to go over here. So we say 500 times 30 plus 800 times 35 plus 1,300 times 25 gives us 75,500. Then the next one, 500 times 5 plus 800 times 8 plus 1,300 times 15. This is 28,400. Okay, then if you did the same thing with the second row, here you should end up with 3,150, then 43,500, and 15,700. So always try and understand what the different elements of your matrix are. So this is the amount of plush for LA. Okay, this is the amount of plush for Seattle, and so on. Right, so that is the first question. Then the second question, back, it says the total cost of material incurred by each plant and the total cost of material incurred by Ace Novelty in fulfilling the order. So now that we know how much plush, stuffing, and trimming we are going to need, what we need to do is multiply by the cost of each material. So we're going to have to multiply the two matrices. Notice that this is plush, this is stuffing, this is trimming, and this is a 3x1 matrix, and this is a 2x3 matrix. So the only way that it's possible to multiply them is if I put this matrix on the side. If I put it on this side, they won't multiply because 1 is not equal to 2. But when I put it on the other side, then I'm able to get a product. So then costs, you have our matrix here. Then you put your cost material on your cost matrix on the side. So we have 450, 0, 0, 0. Okay, and you want to test and check, am I multiplying plush with plush cost? So we know this is plush, this is stuffing, this is trimming. So how do we multiply? It's row with a, this is a plush cost, this is a stuffing cost, this is a trimming. So if I multiply this row, this column, plush will multiply with the price of plush, stuffing will multiply with stuffing cost, trimming here I will multiply. So my matrix that I will get makes sense. Okay, so this is, like I say, this is a 2 by 3 matrix. This is a 3 by 1 matrix. So these numbers are the same, and our answer should be a 2 by 1 matrix. So this is LA, and this is Seattle. So when I get this value here, that is the total cost for LA, and the one here will be the total cost of Seattle. Okay, so we take our calculator again. Then we multiply, say 5,600 times 4.5 plus 7,500 times 1 plus 28,400 times 0.25. Okay, and then we get 29,850. 39,950. And then we do the same thing for the other one. So get 22,450. So we can then say the cost for LA is 39,850. And then the cost for Seattle. All right, and then the final question was, what is the total cost of the to the company? The total cost is just the LA cost plus the Seattle cost. Say that the total cost is 300. Okay, so that is the total cost that is incurred by the company. Right, so with these questions, just make sure that you read them carefully and you understand them. And when you have to multiply matrices, make sure that what you're multiplying with, they make sense. Like here, make sure this is plush, it's multiplying with a plush something. Stuffing is multiplying with a stuffing something. Trimming is multiplying with a trimming, and so on. All right, so we then move on to additive, identity, and additive inverse. Additive, identity, and the additive inverse. Okay, now the additive inverse, sorry, the additive identity first. Now the additive identity is just a zero matrix with the same order as the matrix whose additive let me say that again. An additive identity of a matrix. This is a zero matrix with the same order as the matrix whose additive identity you're trying to find. Okay, so let's say I have a matrix A. A is n M by N matrix. That means it has N rows and N columns. Its additive identity is the zero matrix with order M by N. Okay, so basically what we want to do is add a matrix to A and the answer still equal to A. So with numbers, the additive identity is 0 because when we add 0 to anything, the answer is that same number you started with. So in matrices, the idea is the same. Okay, what matrix can I add to any matrix? And then the answer is the matrix that I started with, and that's the 0 matrix with the same order. So you can see an example of this. Let's say A is this matrix 1, 2, 3, 4. The additive identity of this matrix is the 0 matrix with order 2 by 2. And this just looks like this 0, 0, 0, 0. Because when I add A with this 0, 2 by 2, this is going to be 1, you add the corresponding elements, 2 plus 0, plus 0, 4 plus 0, and this gives me the same matrix I started with, and this is equal to A, okay? Now, we also have the additive inverse. Now, the additive inverse, this is a matrix that when you add it to the first matrix you started with, you get the 0 matrix, okay? So we say that if A is an M by N matrix, its additive inverse is minus A. Okay, so negative of A, so there's a -1 here. You multiply every element in that matrix, and when you add them, A plus minus A, this gives you the 0 matrix. So basically what we want to do is, if I give you a matrix and I ask you what is its additive inverse, I'm saying find me a matrix that when I add these two together, I'm going to get the 0 matrix. Okay, so for example, if I have my matrix A as above, this is 1, 2, 3, 4. I want to find a matrix. So I'll write the A plus, I don't know what the matrix is, X, and then I want to end up with the 0 matrix. So I want to show you how do we get this minus A. So what we do is we can write this down. This is 1, 2, 3, 4, and then X, I'll just put the letters A, C, D, because I need to work them out, and this is equal to the 0 matrix, 0, 0, 0. Then we know how to add these two. I have 1 plus A, 2 plus B, 3 plus C, 3 plus D, and this is equal to 0, 0. Then 1 plus A is 0. This means that A is equal to -1. And then 2 plus B is 0. This means that B is -2. And then 3 plus C is 0. This means that C is -3. And should be a 4. And then 4 plus D is equal to 0. This means that it is -4. So our matrix X is actually this matrix, -1, -2, -3, -4. And this is the same as -1 times this matrix here, 1. Okay. But this matrix here, this is 1 times matrix A. Okay, so additive identity, the one we did up here, means the zero matrix with the same order as the matrix that you're looking for. Its additive identity, and then additive inverse is just the negative of the matrix that you started with. Okay, then we have some properties of the additive identity. So we say that if A is an M by N matrix and C is a scalar, then the following are true. Okay, number one, we say that A plus 0 mn. 0 mn just means the order of this zero matrix is m by n. This is equal to A. So you add the zero matrix to any matrix, you'll get the matrix that you started with. Then number two, A plus negative A. This is equal to the zero matrix of the m by n matrix. And then 3, if C times A is equal to the zero matrix, then C is 0, or the matrix is a zero matrix. So there's only two things. Okay, so here you have a scalar multiplying by a matrix, and then you get your answer as the zero matrix. It means the scalar is 0, or the matrix that you multiplied with is 0. Okay, then some examples. Another example is find the additive identity. And additive inverse of matrix M, which is given by 2, 0, minus 3, 5, minus 1, and 11. So the additive identity, say this is just the zero matrix with the order 2 by 3. So 2 by 3, and it looks like this. 0, 0, 0, 0, 0, 0. Because when I add this matrix and that one, I get the same matrix that I started with. Then the additive inverse, this is negative m. So every single element in this matrix, I multiply by negative 1. So I have negative 1 here. I have 2 minus 3 minus 1, 0, 5, 11. And my answer will be negative 2, positive 3, positive 1, 0, negative 5, negative 11. Solve for x. We have 2x minus this matrix here, 1 minus 1, 2 minus 3, 3 and 2. This is equal to 9, 5, 10, 3, minus 7, and 6. So we solve this just like we do any other equation. So this one can go to the other side. So we have 2x This is equal to 9, 5, 10, minus 7, 6, and here it was negative, so on this side we get positive 1, minus 1, 2, 3, 2. Okay, so 2x, you add, this is 10, this is 12, this is minus 4, this is 4, that's a 0, this is 4. Okay, but we're looking for x and not 2x, so we can divide both sides by 2 or multiply by a half. And we have x, this is equal to, every term in the matrix must multiply the scalar, so we have 5, 6, negative 2, 2, 0, and 2. Right. Right, so we also have multiplicative identity. Okay, now multiplicative identity, this is just like the additive identity. When you multiply this matrix with any other matrix, get the matrix that you started with. And this special matrix is the identity or unit matrix. And some of its properties, the identity matrix. So that if it's an F by N matrix, then one, we have A multiplied by IN, this is equal to A, and then 2 IM multiplied by A, this is equal to A. So notice here I have to use different identity matrices. So this one is an N by N, this one is an M by M, because on the left, the number of rows here must be the same as the number of columns here. And because here it's on the right, the number of columns here must be the same as the number of rows of A. Then as a special case, note that if A is an N by N matrix, so it's a square matrix, then we have IN multiplied by A, so it's an identity matrix that's also N by N. This is the same as A times this. So if A is a square matrix, then it doesn't matter which side you multiply the identity on, you're still going to get the matrix A. All right, then look at determinants and inverses of square matrices. Okay, we start with determinants. Okay, so the determinant is an array of elements ordered in rows and columns, always in a square form. So the notation that we use for determinants, the first one we have determinant of A. Sometimes we'll just write it as determinant A. You have what looks like the absolute value of A, and sometimes you will see delta of A. So all of these are just different ways of writing exactly the same thing, which is the determinant. Now, 2 by 2 determinants, these are very simple and easy to get. We say that for a matrix A, so our matrix A, which is a 2 by 2, CD. The determinant of A is worked out. It's first, we can write it like this. This means A, B, C, D. So notice that this is different from that. Here I'm using square brackets, and here I have what looks like absolute values. And how do we work out the determinant? It's the product on the leading diagonal minus the product on the minor diagonal. So A times D minus B times C. Okay, now the determinant is a single number. So every square matrix has a determinant, and that determinant is a single number. Now let's see an example. If you have a matrix B, it says -4, -3, 6, 2. Now we want to work out the determinant of B. Remember, this is another way of writing the determinant. You can use any of these four to represent the determinant. And we say to do that, it's the product on the major diagonal minus the product on the minor diagonal. So this is -8 plus 18, and this gives us 10. So it's always for 2 by 2 matrices, very easy. Product on the major diagonal minus the product on the minor diagonal. Then 3 by 3 determinants are a little bit more complicated, but not too difficult to do. So with the 3 determinant. Okay, so these two methods that we will use to work out this determinant. The first one is the method of cofactors. Okay, now this method of cofactors is very simple. So let's say you have a matrix A. This is A, C, D, E, F, G, H, I. And this determinants, it's only for square matrices. So if your matrix is not a square matrix, then you cannot work out the determinant. So first thing you do is you're going to put like plus, minus, plus, minus, plus, minus, plus, minus, and plus, and so on. Okay, then after that, what you do is you decide whether you're going across a row or across a column. It doesn't matter which one. So I'm choosing row 1. So I choose row 1. So first thing, you can see I put the plus minus. So the first one is always a plus. Then you just keep changing the sign. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So two pluses must not be next to each other, or two minus signs must not be next to each other. Then you decide what are you going across. Is it a row or a column? It doesn't matter. Then I've decided I'm going to go with row 1. So I write down the elements of row 1 with their signs. So A, this is positive, to write it. I'm leaving some space for a reason. Then I have minus B, and then I have plus C. Then with A is in this column and this row. If I were to remove them, you can see I'm left with this 2 by 2 matrix. So I write that in determinant form, E, F, H, I. You don't look at the signs, this plus, minus, you don't look at them, just write down what you have left. And there's a minus here with B. Let me just write the matrix again, C, D, F, G, H, I. Okay, now B, you can see it's in the first row and in the second column. What matrix am I left with? There's D, G, and then there's F and I. Okay, and then C, this matrix. And I remove the row that C is in. I remove the column that C is in. I'm left with this one, D, G, H. And these are just the determinants that I work with. Okay, so what I will do to get the determinant, it's A multiplied by, we said it's major diagonal, so E times I minus, minus F times H, and then here I have a minus B, the determinant, this one minus that one, so it's D times I minus F times G, and then there's a plus here, C, major diagonal, minus the minor, D times H minus E times G. So this number here will give us our determinant for 3 by 3 matrix. Okay, so now let's see an example how we do that. So let's say we have our usual matrix A, which is 1, 2, 4, 5, 6, 7, 8, 9. Okay, so we said first thing, must put the plus minus everywhere. So putting it in red just to emphasize, this is plus minus, plus minus, plus minus. Then we have plus, minus, and plus. Then you choose a row or a column. It doesn't matter which one you choose. So you choose row 1. And then you write down the elements of row 1. The first one, there's a plus, so it's just positive 1. And then I have negative 2. And then I have positive 3. Okay, then I look at 1. I remove the row and the column that it's in. I'm left with 5, 6, 8, 9. And then 2, if I remove the row and column that it's in, I'm left with 4, 6, 7, 8. And 3, if I remove the row and column it's in, I'm left with 4, 5, 7, and 8. Okay, then I work this out. My determinant of A, this is 1 multiplied by 5 times 9, which is 45, minus 6 times 8, which is 48, then minus 2, 4 times 8, this is 32, minus 7 times 6, 7 times 6 is 42, and then 4 times 8, this is 32, minus 7 times 5, which is 35. So this you will type in on the calculator. I have 45 minus 48 minus 2 times 32 minus 42 plus 3 times 32 minus 35. Okay, and then we get here, let me just check. Let me just type it the way it is. 1, 5 times 9 minus 6 times 8 minus 2 times 4 times 9. 4 times 9 minus 7 times 6 plus 3 times 4 times 8 minus 7 times 5. Okay, I'm getting 0. So just make sure you do it correctly. The answer should be 0. Right. Now, like I said, it doesn't matter which row or column you go across or down, your answer you get will be the same. So let's say, just want to see, will we in fact get the same answer if I choose to go down column 2, for example? So if I choose to go down column 2, the determinant of A, I write down the elements in column 2 with the signs. So I have -2, and then I have +5, some space, +5, and then I have -8, right? So then 2, I remove the row and column it's in. I'm left with 4, 6, 7, 8. This is not a, it's a determinant. Okay, so I removed this row and this column. I'm left with 4, 6, 7, 9. Should be 7. I think that was my problem here. It should be a 9. That's why my answer was not right. This is 9, so this is 36. Okay, and then with 5, here I removed the row and column it's in, so I have 1, 3. So I've removed this one and that one, so I have 7 and 9. Then here I remove the row and column 8 is in, so it's this one and that one. So I have 1, 3. I removed this one and this one, and I have 4 and 6. Okay, so my determinant, this is -2 multiplied by 4 times 9 minus 6 times 7 plus 5, 1 times 9 minus 3 times 7, then minus 8, 1 times 6 minus 3 times 4. Now let's see if we still get the same answer. We should if we word it correctly. Otherwise, you need to check, see what we did wrong. So I say -2, 4 times 9 minus 6 times 7 plus 5, 1 times 9, which is just 9, minus 3 times 7, then minus 8, 1 times 6 minus 3 times 4. Okay, and this also gives us 0. So doesn't matter which row or column you choose to go across or down, as long as you follow the method, you will always get the right determinant. Now, why is this useful? It's useful sometimes you have one row or one column that has a lot of zeros. So if you go across that row, then you don't have to do a lot of work, because if I have a 0 here and I have a 0 here, I only need to work out this one there. All right. So that is the first method of finding the determinant using the cofactor method. Then we have what is called the method of diagonals. Now the method of diagonals, we have a matrix A like this, same matrix, A, B, C, F, G, H, and I. Now to find the determinant, it's very easy. What you do is you write the matrix here without the square brackets. You have A, C, D, F, G, H, I. And then you do the same thing here, A, C, F, G, H, and I. Okay, so what we then do is you are going to multiply these three numbers like this. And then these three numbers like this. And these three numbers like that. Okay, so you have A, so our determinant, A. So our determinant of A, we say we multiply A, E, I, then we add B times F times G, and then we add C times D times H. And then we subtract. Now we find matrices in the other way. So here, not matrices, but diagonals. So I have this one here, 1, 2, and 3. Okay, so it's minus C times E times G plus A times F times H, and then V D I. You can see this one here, I never use it, so sometimes you don't even need to write it when you are writing the matrix. So you can just write A, B, C, D, E, F, G, H, I, and then A, B, D, E, F, and H. All right, now let's try it with the same matrix we did and see will we get the same answer. Okay, so we say we write the matrix 1, 2, 3, 5, 6, 7, 8, 9. Then we repeat 1, 2, 3, 6, 9. So then the first one is 1 times 5 times 9. 1 times 5 times 9 plus 2 times 6 times 7 plus 3 times 4 times 8 and then you subtract out the way. Say 7 times 5 times 3 is 1 times 6 times 8 2. Okay. Okay, so we have 1 times 5 times 9 plus 2 times 7 plus 3 times 4 times 8 minus, and brackets here, 7 times 5 times 3 plus 1 times 6 times 8 plus 2 times 4 times 9. Okay, and you can see the answer is still 0. So we're still getting a 0 like we did above with the cofactor method. And let's try another matrix. Let's see, okay, this is plus 1, 1, 0, then 2, 3, 2, 3, 4, the determinant of B. So we said we write the matrix minus 1, 2, 3, 3, 2, 4, 1, 2, 0, 2, 4. Then so this one we didn't even use it, so there's no need to write it. So you can write it or write it. Then say that this product here minus 1 times 3 times 4 plus this here 1 times 2 times 3. And this here 0 times 2 times 3 and minus now 3 times 3 times 0, which will just be 0. And this one here 3 times 2 times negative 1 plus this one here 4 times 2 times 1. Okay, then calculator. Minus 1 times 3 times 4 plus 1 times 2 times 3. Then this term here is 0, so I don't have to write it. Then minus, these brackets here are very important. This term is 0. And then I have 3 times 2 times negative 1 plus 4 times 2 times 1. And the answer is negative 8. Okay, so you can also try find the determinant of this matrix using the cofactor method. You should still get negative 8. All right, so we'll stop there for today. In the next lesson, we will look at finding the indices of matrices.